One of the goals of machine learning models is to take features as inputs and then match the target of the model, or the so-called label. Now, that is the theoretical goal, or the aim in theory. But in reality, what happens is models would take in the features and would construct or yield predictions, and there would be some discrepancy between the predictions and the actual observations. So that's where this diagram is useful. So what we see here on the top is we have features. The features are subject to some rules, and then the rules would lead to a target. But we can call this target, or perhaps observe is more precise. So in this context, there is always going to be a comparison between, you may think of this as between what's observed versus what is predicted. And the prediction is the outcome of a model. It's what the model is an artifact, and something comes out of the model, and that's what we call the prediction. So the idea is that, is there a perfect match? In reality, the perfect match, you should be very skeptical if that's what you're obtaining on your end is too good to be true. In fact, the discrepancy is what would be addressed as the so-called error. So the error is a difference, and that difference is when you compare prediction and observation. So you may literally take the subtraction of one from the other. You can take absolute value of the subtraction. You can consider absolute value in higher dimensions is generalized with norm of a vector. So the square of the norm of a difference between observations and predictions. Those are the kind of metrics that are used to quantify the discrepancies, quantify the error. Very importantly, one of the aims is precisely to train. This is what I'm putting my cursor here. Do more training. That means feed models with more input features. Do more training, but now do that training driven by getting the error as small as possible. That's it's a really good way of phrasing this. So getting the error as small as possible. So small errors, by small errors, we are going to mean minimization here. So in other words, we would like to translate that into minimize the discrepancy, minimize the error. Okay, so this turns into an optimization problem in mathematical terms. So we are saying that a machine learning model would have discrepancies, and these discrepancies, these differences, these errors would depend on the predictions the model can generate. So the model would have the so-called parameters, and now this optimization problem, the finding optimal, in the vocabulary of optimization, you would like to define a function and would like to address as to whether the function attains its minimum value or maximum value over some subdomain. And when these extreme values, extrema that they're called, when they occur, so that there is an optimal value for the function. So in this case, the function under consideration is what's denoted here with f as a function of w, where w is denoting the model parameters, because in many cases those parameters are going to in many cases, those parameters will be considered as weights. Now, this error function is also commonly in this context called cost function. That's terminology from optimization. Also, this may be known as the objective of the optimization. So we may call it error function, objective function, cost function, and the goal is to find minimizers or maximizers, values, to find candidates, members of the domain of the function where the function would attain one of these extreme values. So in symbols, we would write something like, we're interested in the minimization of a function f of w. Is this problem we're writing here on the lower left corner of the screen. And the optimal model of machine learning would be one that produces or yields the lowest possible error. So in other words, when a specific value of w, which I'm gonna call here something like w hat, I'm gonna say that the w hat is the optimizer, because this is also some mathematical notation. If we're interested in the minimization problem, this value of w hat would give the minimum value, that arg argument min f of w. So this means that when f is evaluated at that value of w, and this is of course w ranging on some region domain S, when f is evaluated at that value of w, we call w hat, then f attains a minimum value, optimal value, that is. And that's what we would consider the best model or optimal model. So the machine learning main problem is to find parameters that would give this optimal model, in the sense of a model that yields or produces the lowest possible error, or the lowest or smallest discrepancies between the observations and the model predictions.